So this is Anthony Raj from NEET Gateway. So we will discuss about chemical equilibrium. So the equilibrium is attained by reversible reactions. Okay. So naturally, some reactions are reversible. That means, so generally, if you take a reaction, so we'll start the reactants. Okay, it will go to completion and give products. So at the end of the reaction, the reactants will not be there, only the products will be there. So there are some reactions which are reversible. That means the reactions happen in both forward and reverse direction. Okay, say we start with reactants, okay, it slowly reacts to give products. Okay, now once the products are formed, they give back the reactants. So these reactions will never go to completion. Okay, so the final state of this reaction is the equilibrium state. Okay, now what is the equilibrium state? In the equilibrium state, there are two reactions happening. Okay, one is a forward reaction. Okay, reactants giving products, and there is a reverse reaction where the products react back to give, reactants. Okay, so therefore there are two reactions happening in opposite directions, but it attains equilibrium. Okay, so when we say that the system is at an equilibrium, when the rate of forward reaction becomes equal to the rate of reverse reaction. So at this stage, the amount of reactants react to give products, okay, is equal to the amount of products they react to give the reactants. Therefore, at this point, if you watch the macroscopic properties like concentration, okay, that will remain constant. That does not mean that the system is static, the system is dynamics. Even now the reactants are reacting to give products, the products are reacting to give the reactants, but in both directions the rate will be same. Okay, that is why we cannot see any macroscopic changes. That is, the concentration of reactant products remain constant. So the main point is, at equilibrium, the rate of forward reaction becomes equal to rate of reverse reaction. So we can take a general reaction, right? So A plus B giving C plus D, which is reversible. Okay. So here the reactants react to give products and the products will give back reactants. We take a simple equation for now. Okay. Right. So the rate of forward reaction, okay, we can say the rate constant forward reaction is Kf and the rate constant for reverse reaction will be Kr. Okay. Okay. Or the rate of forward reaction will be Rf, rate of reverse reaction is Rr. The rate of forward reaction becomes equal to rate of backward reaction. Okay. So now I will slightly change this equation with stoichiometric coefficients. Say we take a reaction like A times A plus B times B, okay, so reversible, giving C times C and D times D. So small a, small b, small c, small d are the stoichiometric coefficients. So for example, if you take this reaction, suppose N2 gas plus 3H2 gas, okay, reversibly giving 2NH3 gas. Okay. Now the stoichiometric coefficients are, for nitrogen it is 1, for hydrogen it is 3, for NH3 it is 2. So small a, b, c, d represents these stoichiometric coefficients. Okay. So first I will simply say how do we write the rate constant. We are going to study in detail about that. The rate constant K, okay, is based on concentration is written as, okay, concentration of C to the power of small c, D power small d divided by A power small a, B power small b, and all of them are equilibrium concentrations. That is, when the system attains equilibrium, okay, and the concentrations become constant, okay, they don't change, that is called equilibrium concentration. So that we have to substitute in this equation to get equilibrium constant. Okay, this is based on concentration. We are going to study about this detail in a short while. Right. This equilibrium constant changes only with temperature. Okay, they don't depend upon initial concentrations. Okay, so if you take in the correct ratio of concentration of reactants, the equilibrium constant will not change. Whatever be the initial concentration does not depend upon that. Okay, so the equilibrium constant mainly changes, okay, with temperature only. So that you have to find. Okay, so another important point is being an equilibrium reaction where there is a forward reverse reaction which can be done from either side. Okay, say for example, we have taken this Haber's process. This process, Haber's process of preparing ammonia. Okay, so I have written this equation, right? So now we have written these are the reactants. We start with this, and the products will be formed. So when the product concentration increases, it will give back the reactants, right? Okay, but the equilibrium can be started from the product side also. We can first take NS3. If you take, then they will give, okay, N2 and 3H2 as the products and give back the reactants. Okay, so the equilibrium can be started from either side, right? Being a reversible reaction, even if you take the products first, then they'll give the reactants as the products and vice versa, right? That is another point should be noted. Now we will see some characteristics of chemical equilibrium, right? So you must know, if you add catalyst which does not alter the equilibrium state. Okay, when we say equilibrium state, we say the relative concentration of products and reactants. That is the equilibrium state where the equilibrium constant, okay, remains the same, does not change. So addition of catalyst does not alter the equilibrium state. Okay, so the catalyst only helps to attain the equilibrium faster. If you use a catalyst, we will attain the equilibrium state faster than without catalyst. Okay, so for that only we are using the catalyst. Then equilibrium concentrations can be changed by change in concentration of reactant and product. So the relative concentrations will remain the same. That is, the equilibrium constant remains the same. Okay, we can change in concentration reactant product will change the equilibrium concentrations. Okay, by changing pressure, again you can change the equilibrium concentrations, but again the equilibrium constant does not change because the relative concentration of products and reactants will remain the same. Okay, but if you change the temperature, okay, then the equilibrium shifts to another state of equilibrium, okay, where the equilibrium constant actually changes, right? Because the reactions will be exothermic and endothermic. In a reversible reaction, you must note that if the forward reaction is exothermic, that is, it releases heat, the reverse reaction will be endothermic, right? Okay, and vice versa. Okay, right. So now if you change the temperature, okay, the equilibrium will shift. Suppose if you increase the temperature, you are giving heat, therefore the endothermic part of the reaction will happen faster, right? So suppose if you are reducing temperature, that is, you are cooling the system, you are removing heat, then the exothermic part will happen faster. Therefore the equilibrium will get shifted to another equilibrium state. Therefore the equilibrium constant will also change when you change temperature. Okay, right. So I have already given this example, the Haber's process example. So the point is, suppose if you add more N2 and more H2, then more NS3 will be formed. Therefore the reverse reaction will also happen. So the equilibrium concentrations will change, but still the equilibrium constant Kc will not change. That is NS3, okay, square bracket means concentration, power divided by, so N2, okay, then H2 power 3. Okay, the relative concentrations or the equilibrium constant will not change by changing the concentration of reactants. So if you take them in the stoichiometric ratio, right? Okay, so we are going to study about the change in pressure, temperature, okay, using Lee-Chartier's principle later. So there we will explain how it influences the forward reaction, backward reactions. So those details we will discuss with Lee-Chartier's principle. Okay, for now you can change the equilibrium concentrations by changing these parameters, and the equilibrium constant itself can be changed by changing the temperature. Okay, right. Okay, right. So now we have to study the law of mass action. Well, generally, so law of mass action is the rate of a reaction is proportional to the product of active mass of the reactants raised to suitable powers. Okay, that is law of mass action. Okay, so the active masses, okay, very very important, that's why it's called law of mass action. Okay, law of mass action. The law of mass action, the rate of reactions are proportional to the product of active masses of reactants. Okay, these active masses are proportional to concentration. Okay, and for gaseous systems, it is proportional to the partial pressure. Okay, so the active mass, say for reactant A, which is proportional to the concentration of A, or it is proportional to the partial pressure of A for gaseous reactions. For gaseous reactions. Okay, they are not exactly same, okay, but they are proportional. Okay, so in place of active masses, we can use concentration or partial pressure. Here I have taken an imaginary reactant A. Okay, that's okay. Right. The active mass proportional to concentration. This I already told you. Okay, so for a general equation, so this is the equilibrium constant equal to Kc, okay, which is equal to Kf by Kb. Okay, maybe I can slightly explain this. Okay, for a rate of forward reaction, it will be Kf into, okay, reactants A power A, equilibrium power A, B, equilibrium concentration B. For rate of reverse reaction, it will be K reverse, okay, rate constant for reverse, then C power small c equilibrium and D power small d equilibrium. Okay, so we have told you in the previous slide itself, the rate of forward reaction becomes equal to rate of reverse reaction. If you equate them to, we'll get like this, okay, which will be Kf into A power A, B power B, which is equal to Kr into C power C, D power D. So here A, B, C, D are the equilibrium concentrations. So now we can modify, we can slightly change Kf by Kr is equal to C power C, D power D divided by A power A, B power B, which is equal to Kc. So Kc means equilibrium constant based on concentration. Okay, that is how we get this equation. Okay, that is by equating the rate of forward reaction on the rate of reverse reaction. Okay, we get this, right? Okay, right. Okay, so this condition, rate of forward reaction becomes equal to rate of reverse reaction. It is even be true for multi-step reactions, that is kind of complex reactions. Okay, so the equilibrium does not depend upon the reaction mechanism. Okay, it is assumed that, okay, if you take a multi-step reactions, at every step, okay, the rate of forward reaction becomes equal to rate of reaction, which does not depend upon the reaction mechanism. Okay, it is assumed that way. So even for multi-step reactions, okay, where the reversibility is there, so the overall reaction can be taken as a equilibrium reactions, and this particular law can be applied. Okay, so even for multi-step reactions, irrespective of the reaction mechanism, okay, it can be considered to be at the equilibrium state. Okay, very important point to note. Right. So next, the equilibrium state has minimum Gibbs energy. Right. The equilibrium reactions proceed up to the equilibrium state spontaneously. Okay, up to the equilibrium state, it will happen spontaneously. Okay, so it's a spontaneous reaction up to equilibrium state. So therefore, as it is spontaneous, it will reach a minimum energy state where the Gibbs energy will be minimum at the equilibrium state. Okay, then this I already told you, it is independent of initial concentration. If you take them in the stoichiometric ratio, okay, and it does not change only with temperature, right? Okay, so as we are discussing the concentration, okay, of the reactants and products, right? So if you take a pure solid or a pure liquid, okay, then it can be ignored in the equilibrium reaction. Okay, like say for example, so if I take a reaction like this, So calcium carbonate, okay, solid, reversibly giving calcium oxide, solid, plus carbon dioxide, gas. Right? So if you have to write the equilibrium constant Kc, which will be calcium oxide product on the numerator and the reactant on the denominator, calcium carbonate. Okay, so now this calcium carbonate and calcium oxide are pure solids. Okay, so the concentration does not apply to them. So therefore, I can simply leave them and write Kc is equal to CO2. So in the equilibrium formula or the equilibrium constant equation, okay, so we can ignore the pure liquid and pure solids. Okay, right. So you can include the gases, then the solutions like the concentration, right? Terms you can include, but the pure solid and pure liquid you can ignore, right? Okay, so I told you Kc is the equilibrium constant based on concentration. Similarly, for gaseous systems, we can also use another equilibrium constant equation, which is Kp. Okay, so for the general equation what I have taken, okay, we can take Pc is positive pressure of C, positive pressure of D, positive pressure of A and positive pressure of B. Okay, so you know that the positive pressure is proportional to the mole fraction and mole fraction is a concentration term. So therefore, positive pressure is proportional to concentration. So for gases, we can use partial pressures also, okay, instead of concentration. Okay, so this Kp based on partial pressure, which is true only for gaseous systems, like we have seen for Haber's process, right? Okay, for the preparation of ammonia, okay, like that. If you take the gaseous systems, then we can use partial pressure instead of concentration. Okay, right. So now I want to give you one more example. Listen. Now I want to give you a graphical representation, okay, of this equilibrium state. Please listen carefully. Okay. Okay. So I take a simple equation, say one reactant A, say giving reversible B. Okay. We start from the reactant side. Okay, this is concentration. So this will be time. This will be time. Okay. Now the concentration of A, say we start from here. So the concentration of A will slowly decrease during the reaction. Okay. Similarly, the concentration of B being a product, initially it is 0 and it is gradually increasing. Right? So you can see in the graph that so both graph gets flattens after some time. So this state is the equilibrium state where the concentrations become constant. Okay. So similarly, I have told you that the equilibrium reactions can be started from either side, from the reactants or products. I take another example. The example is say H2 gas plus I2 gas, okay, reversibly giving 2HI. Okay. Now say we start from the reactant side, then H2I2, I start from here and it will gradually decrease. Okay. Then reactants, they can increase, okay, and it again gets flattens, right? Alright. So this is H2 plus I2, concentration stoichiometrically taken. So this one is concentration of HI which increases. Now I will tell you, okay, if you start from the product side, okay, then what we do, we start from HI, okay. Again, so this is HI concentration, okay, I am starting from there, therefore at maximum, right. Okay, here the reactants will be 0 initially and we start from reactants and reaches here. This has 2 plus I2. Because this is reverse. Okay, I am starting from HI, so that is the concentration HI is maximum and gradually reduces and flattens. Okay. Similarly, here the products are H2 and I2, they start from 0, they slowly increase. So this point is the equilibrium point where the concentrations become constant. Okay. So here we have this, from this side Okay, we are starting from reactant side. Okay, the same reaction from the product side also we can start. Okay, so take HI and gradually decreases, then H2I2 will be starting from 0, and at a particular point the concentrations become constant. Okay, so okay, there are some different graphical representation. I have given you only the 2 graphs given in the NCERT book. Okay, there are some other types of representation also. Okay, basically we are starting from a product side or the reactant side. Okay, and after some time, after attaining equilibrium, the concentration terms will become constant, which will become flat. Okay, so that point is the equilibrium point. Alright? Okay. So now we have learned 2 different equilibrium constants. One is Kc, which is based upon concentration, okay, and Kp, which is based upon partial pressure. So for gaseous systems, so both equilibrium constant types can be used. So we have to derive a relationship between them. Right? Okay. So for this, we are assuming that the gases in the system are ideal. Therefore, I can write, okay, say I take the general example only. Okay, I take the general example only. So A times A plus B times B, all of them are gases, giving C times C. Okay, C times C, C times C plus D times D. Okay, right. So Kc is equal to C power C, D power D by A power A, B power B. We assume that A, B, C are ideal gases. For ideal gas, I can write P is equal to N by V into RT. Okay, so this is partial pressure. So N by V we know is a concentration, number of moles per volume, that is concentration. So for PA, I can write this is concentration A, okay, into RT. Okay, if PA power A, then I can write A power A, okay, RT power A, right? Okay, like that I can write for, okay, PB, PC, PD also. Okay, I will try to write PB power B is equal to B power B, okay, RT power B. Okay. Similarly for PC and PD also I can write. Okay, if you write that way, then Kp is equal to, okay, left hand side, so Kp will be actually, so PC power C, PD power D divided by PA power A and BB power B. Right? Okay, so right hand side you see the constant terms are there. So concentration of C, concentration of D power D. So this will be actually our Kc. Okay, what is the extra term there? RT. Right? So RT power C and D will be the numerator and RD power A and B will be the denominator. Right? That's the extra term here. So therefore, if you simplify that, you will get RT power C plus D minus A plus B. Okay. So this is the number of moles of products, total number of moles of products minus total number of moles of reactants. That will be the change in the gaseous moles of product minus reactants. Okay. So Kp is this. So in that place, for Pa you have to substitute this Pb, and Pc, Pd also you can substitute, right? Okay. So the Pc will be equal to C power C, RT power C. Similarly, so Pd power D will be D power D, RT power D. Okay, we substitute them accordingly, you will get this equation. Okay, this is the difference in number of moles of gaseous products minus gaseous reactants. So Kp is equal to Kc, RT power, this delta Ng is this one. So this is number of gaseous moles of products minus number of gaseous moles of reactants. Alright? Okay. So now from the equation you can see, if delta Ng is 0, then RT power 0, which is equal to 1, so Kp will be equal to Kc. Right? Right? If delta Ng is 0, okay, then RT power 0 is 1, then Kp will become equal to Kc. If delta Ng is positive, then what it becomes? Kp is equal to, so Kc, RT power, a positive value. Okay, there will be a positive value, say which will be say 2 or 3. Okay, I just take an example. So if you multiply Kc by some number, you are getting Kp, right? Okay, so the RT will be a positive number, so it is square will give Kp, so therefore naturally Kp will be greater than Kc, because with Kc multiplied by a number, you get Kp. Okay, similarly, if delta N is negative, say I take Kp is equal to Kc, if I take RT power, say minus 2 now, it will becomes Kc divided by RT square. Now if you divide Kc by a number, you get Kp. Okay, if you divide Kc by a number, you get Kp, therefore Kp will be less than Kc. Okay, so when you find out delta Ng, where the G means the gas only. In any reaction, when you calculate delta Ng, be careful, the number of gases moles of product, only gases products, minus the number of gases moles of reactants, that is delta Ng. Okay, that you have to substitute here. So Kp is equal to Kc RT power delta Ng, very, very important. Kp is the equilibrium constant based on partial pressure and Kc is based on concentration. R is gas constant, T temperature in Kelvin, and delta Ng, as you know, it's a difference in number of gases moles of products and reactants. Okay, right, I think it's very clear. So now we must clearly, know, right? So what this equilibrium constant signifies, right? Okay, from equilibrium constant, what can we know? Okay, so the equilibrium reaction, okay, so there are some three important different types of equilibrium reaction. They're not types, but there can be three different ways they react. Okay, so the magnitude of K, the value of K is the indicator of extent of a reaction. Now listen carefully. I take a simple reaction, take A plus B, reversibly gives C plus D. We know in the K equation, the products are in the numerator and the reactants are in the denominator. Okay, so the product constant increases, K value increases. If the reactant constant decreases, then also the K value increases. Okay, so I take only simple K will be, so CD by AB for this reaction. Okay, so therefore, if the product constant increases, K will increase. Okay, if the reactant constant decreases also, K will increase. So if there is a large value of K, that means if the K value is very large, that means that so more products are formed, okay, the reactants are very less. Okay, so we can say it almost goes to completion, but it is very high. The K value is very high, we can say it almost goes to completion. Okay, so the K value is more simply means it happens the forward direction more and reverse direction less. Okay, I can write like this, which is A plus B. Okay, if K value is more, then forward happens more to give C and D, reverse only less. Okay, so if the K value is more, that indicates the reaction happens much more in the forward direction than the reverse direction. Okay, if K value is large, that means the reaction almost goes to completion. There are no reactants at all, only products. Okay, right. Then if the K value is low, then the next case is K value is low. That means when K value will be low, K is equal to CD divided by AB. Okay, so if the products are less, then K will decrease. If the reactants are more also, the K will decrease. So please note that these are equilibrium concentrations. After attaining equilibrium only we are taking these values. Okay, at the equilibrium the products are less, then K value will be less. At the equilibrium the reactants are more, then the K will be less. So the K value less simply means the reaction proceeds only to some extent in the forward direction. Okay, or the reverse reaction happens more. Okay, if there is a very less K value, then the reaction does not proceed at all in the forward direction. Okay, the reverse reaction only happens more in the forward direction, which does not proceed at all. So that is what is indicated by the lower K value. Okay. The intermediate values, the K value is between 10 power 3. Okay, if the K value is between 10 power 3, okay, which is more than say 10 power minus 3. Okay, if it is in this range, okay, if it is have a moderate value, not very high, not very low. So in that case, there is a comparable amount of reactants and products. Okay, so K value importantly indicates to what extent the forward reaction proceeds or to what extent the reverse reaction happens, that can be indicated by the K value. Okay. So the K value indicates the extent of the reaction. Okay. So please note that, okay, at equilibrium state, the rate of forward reaction becomes equal to rate of reverse reaction. That's all. Okay. It does not mean that, okay, equal number of reactant products are formed. It simply means the rate of forward reaction becomes equal to rate of reverse reaction at the equilibrium state. Okay. So therefore, so using K value, you can clearly say what is the extent of reaction, to what extent the forward reaction happens, to what extent the reverse reaction happens. That is one of the important application of the equilibrium constant. Okay, right. So from this lesson, okay, in NEET as well as your NCERT board exam, okay, problems are asked. Okay, in this, from this lesson, okay, in NEET as well as in NCERT board exam or the CBSE board exam, okay, some problems are asked. So very, very important chapter. You must understand the concept clearly to solve these problems. Now we will take some example problems. Okay, so the equilibrium constant for the following reactions are given. Then find the equilibrium constant for this reaction. Okay, so first we will try to write the equilibrium constant. Okay, K1 for this reaction, right? Okay, K1 is equal to, so first the product, so NH3 in the numerator to the power of stoichiometric coefficient divided by N2, okay, H2 power 3. This is K1, right? So simply for this equation, I have written the K value, right? Then second one, K2 is equal to, so NO in the numerator, okay, square divided by N2 O2. Okay, then K3 H2O divided by H2 O2 power of. Okay, these three values are given and you are asked to find out the equilibrium constant for this equation. So what do we need? Okay, these are given and we need K for this equation. It is NO square H2O thrice divided by NH3 power 2 O2 power 5 by 2. Okay, right? So for this we need the equilibrium constant. Okay, now compare these reactions. Listen, the NO2 square is here, the NO2 square is there. So the NO2 is not there in any other reaction. Okay, so therefore we can say the K will be equal to K2. Okay, K2 simply NO2 square is there. Then you look at H2O. H2O cube is there, but in this equation the H2O is here in the numerator, right? Right? So but no other equation H2O is there. So H2O cube, that means we can say which is K3 cube. Okay. Then look at this, NH3 square is in the denominator. Okay, here the NH3 square is there in K1. In no other equation it is there. So therefore I can say K1 square, right? Okay. So now we will try to see. Okay, so it seems like this only. Now we will write and see whether we are getting the this K value. K2, which is NO2 square, NO square, which is NO square, NO square K2 divided by N2 and O2. Okay. Then K3 cube, that is H2O cube divided by H2 cube. Okay. Then O2 cube, which is O3 by 2, right? Divided by K2 K1 square, which is NH3 square divided by N2 and H2 cube, right? Okay. So now we can cancel this N2 and N2 can be cancelled. H2 cube can be cancelled. Okay, right. So now if you see, we get NO square H2O cube divided by, we have NH3 square O2 power 1 plus 3 by 2. So it becomes O2 5 by 2, which is equal to the K what we need. Okay. So like this the problems can be asked, because the equilibrium constant equations can be algebraically manipulated like this. Okay. So first you write the equilibrium constant expressions for the given equations, then write the equilibrium constant expression for, okay, what has been asked, the equation for what has been asked, then you calculate like this. Okay. Maybe two or three more examples you can do and practice this. Okay. From the given equilibrium constant equations, how to get the equilibrium constant for the new equation for which the relationship is asked. Okay. Right. So we will do one more problem. So this problem is also very important. Given that the equilibrium constant for the reaction, right? Okay. You are given like this. Okay. For this equation, the equilibrium constant is 278, right? So we'll write K. So K is equal to SO3 square divided by, okay, SO2 square O2. Okay. So the value is 278, right? Okay. Right. Okay. So now you are asked for the equilibrium constant for this equation, right? So before that, I want to tell you one simple rule. Listen carefully. Suppose for H2 gas, okay, plus I2 gas giving, okay, 2HI gas. Okay. So if the K value is, K is HI square divided by H2 I2. Okay. Now if I modify this equation like this, NH2 gas plus NI2 gas reversible 2NHI gas. Okay. Right. Now if you write K dash for this, K dash is HI power 2n, okay, H2 power n and I2 power n, right? Now if you compare these two equations, okay, I will simply multiply it by n. Number 1 if you take this, and number 2 is simply 1 multiplied by n, right? Okay, so if that is the case, then K dash becomes, okay, 2 is there 2n, 1 is there power n, 1 is there power n. So it simply becomes equal to K power n. Okay. So if you multiply the equilibrium equation by n, then the equilibrium constant becomes power n. Right. Similarly, if you divide this equation by n, then the equilibrium constant is power 1 by n. Right. Are you able to understand this? Okay. So this you must remember. Right. So if you multiply the equilibrium equation by n, then the equilibrium constant is power n. Divide by n, then power 1 by n. Right. So now similarly only we are going to solve this problem. So now what has been asked is for this equation, SO3 gas reversible SO2 gas plus of O2 gas. You write K dash for this. K dash is SO2 in the numerator, then O2 power 1 by 2, okay, divided by SO3, okay, that's all. Right, this is K dash. Now you compare these two. Okay, what has happened? Okay, this SO3 is numerator, here is the denominator. SO2 the denominator, here is the numerator. O2, okay, therefore, the first we must know that, so it's a reciprocal of K, right? Correct. SO2 numerator, here denominator. SO2 denominator, here numerator. So it is 1 by K first. Okay, it has been 1 by K. Then if you see, after taking 1 by K, here 2 is there, but here only 1 is there. SO2, 2 power 1 is there. O power 1 power half. Therefore, reciprocal and root. Okay, right? So that is, if you multiply this equation by 1 by 2 and reverse that, we get this equation. Okay, right? You are dividing this equation by 2, then you reverse, then you get the needed equation. Okay, so therefore, are you able to understand this? Okay, it has been the reciprocal, that is a reverse reaction Okay, because SO3 in the product, here reactant. Okay, SO2, O2 in the reactant, here the product. Then it has been divided by 2. Okay, therefore, right, this is root 1 by K or root 278, 1 by 278 root. So if you find out, that is the answer. Okay, so like this, algebraically, okay, if you multiply equation by 2, then the equilibrium constant expression power 2. Divide by 2, power 1 by 2. Okay, if you reverse, it is reciprocal. Okay, so that I think you can see and clearly understand. Okay, right. So now we will do one more problem. The dissociation constant of acetic acid and HCN at 25 degrees centigrade are given. Right, find the equilibrium constant for the reaction. Right, first we will write the dissociation equation for acetic acid and HCN. Okay, so acetic acid CH3 COOH. Okay, reversibly it gives CH3 COO minus plus H plus. Okay, so the K value, let us say we write as K1, right? K1, which is CH3 COO minus H plus divided by, okay, CH3 COOH, which is equal to, this is the dissociation of acetic acid, the dissociation constant is K1, right? I have written the equation in K1, which is equal to 1.5 into 10 power minus 5. Okay, and for HCN similarly, which is another weak acid, HCN reversible, we get H plus Cn minus. So let's say it's K2, so we take it as 1, so this is 2, K2 is equal to H plus and Cn minus divided by HCN. Okay, okay. So which is equal to, the value is 4.5 into 10 power minus 10. Now, what do we need for this reaction? Okay, now for this reaction, I will write K, I simply write K. K is equal to HCN, okay, CH3 COO minus divided by, this is what I need, Cn minus, okay, CH3 COOH. Okay, now we have to compare, okay, these two equations. Okay, look at this, COO minus the numerator, here also numerator, right? CH3 COOH denominator, here also denominator. Okay, so therefore, and there is no square or any power there, so it is simply K1, which is in the numerator, right? It has not changed, right? Now look at this, HCN in the denominator, here numerator, Cn minus numerator, denominator, no powers, no power 1 by 2, no division. Okay, now it will be divided by K2. Okay, maybe, okay, we have done this, now you can slightly check. Okay, let me check this. What is K1, which is CH3 COO minus, okay, H plus divided by CH3 COOH divided by K2 is H plus, okay, Cn minus divided by HCN. Okay, so H plus gets cancelled, and if you so HCN will come to the numerator, Cn in denominator. So you get this equation. Okay, it is simply K1 by K2, which is simply K1 by K2. Now substitute the values, which will be 1.5 into 10 power minus 5 divided by 4.5 into 10 power minus 10. Okay, so it will be 1 by 3 minus 10 come to numerator plus 10. So 1 by 3 into, okay, so it will be, okay, this is 3 times. So 1 by 3 into minus 10, so 10 power minus 5, this will be plus 10, which is 1 by 3 is 3.33 into 10 power 5. That will be the answer, right? So like this, if you are given some equilibrium systems, for that you can write the equilibrium constant, and if you are asked for another equation, then using that K1 and K2, you must be able to, okay, write the equilibrium constant for the given equation, okay, for the equation for which the constant is asked. Okay, so this type of questions have been asked in NEET. Okay, I think this type of question will be asked in CBSE board also, I think. Okay, so using the equilibrium constant expressions, okay, and the reversible equilibrium equations, okay, you can manipulate and find out the equilibrium constant values. Okay, okay, so I think you have understood this. Okay, right. Okay, so look at this example. For the reaction 2A plus B gives 3C plus D is begin with the concentration of A and B both at the initial value of 1 m. When the equilibrium is reached, the concentration D is found to be 0.25. Okay. Okay, right. First you write simply the reactants A, B, C, D. Okay, right. So this is the equation. Then it is begin with the concentration A, B both at 1 m. So initial. So this is 1 m and this is 1 m. So C and D are not there, right? Initially. Now the reaction proceeds. Okay, so the forward reaction happens. The products are formed. Now the reverse reaction also happened. Okay, so it attains equilibrium state. At equilibrium state, okay, it has been told that the concentration of D is found to be 0.25. So this one is 0.25, right? This one is 0.25, right? Okay. So now look at this equation. At equilibrium, if D is 0.25, okay, C will be 3 times the D, right? Can you see that? D is 0.25, then C will be 3 times D. Therefore, C will be 3 into 0.25. Okay. Now look at B. If 1B reacts, then 1D will be formed. If 1B reacts, 1D will be formed. Therefore, if 0.25D is formed, then 0.25 reacted from B. Okay. So this is reactants, the products, right? This is 0.25. So stoichiometrically this is 3 times products. So the reactants, products. Okay, right. Okay. So now coming to B, 1B reacts, 1D is formed. So 0.25D is present. So 0.25 of B has reacted. Okay. Similarly, come to A, right? If 2A reacts, 1D is formed. Therefore, 1 minus 2 into 0.25. Okay. Only if 2 into 0.5 reacts. Okay. Okay. 1 minus, okay, 2 into 0.25. Okay. Right? Are you able to understand this? Okay. So D is 0.25. Stoichiometrically 3 times will be C. If 1B reacts, 1D is formed. If it is 0.25, then B reacted is 0.25. Right? So 2A gives D. If 0.2 is formed, then 2 into 0.25 of A would have been reacted. Therefore, so 1 minus 0.5, it is 0.5. This is 0.75. Okay, here it is 0.75, 0.25. Okay, now we can find out the equilibrium constant according to the equation. The K will be equal to C power 3 D divided by, okay, A power 2 into B. So according to this equation, you have to write the equilibrium constant. So which will be equal to 0.75 cube into 0.25 divided by A square. A is 0.5 square, B will be 0.75. Okay. So now 0.75 you can cancel. Okay, one cancel. So it becomes 0.75 square into 0.25 divided by 0.5 into 0.5. So I can write like this: 0.75 into 0.75 into 0.25 divided by 0.5 into 0.5. Maybe numerator I can make it into full number. So that is multiply by 10 by 10 by 10 by 10. So 7.5 into 7.5 into 0.25 divided by 5 into 5. If you cancel it, it will become 1.5. So this will also become 1.5. Okay, you cancel this. So the answer will be 1.5 into 1.5 into 0.5. So if you multiply, you will get the answer. Okay. Are you able to follow this? Okay. So if you are given one of the equilibrium concentrations, okay, and initial concentration of the reactants. Okay, then you can stoichiometrically find out what will be these will be the equilibrium concentrations. Okay, so the last line will be equilibrium concentrations. If you know them, then substitute in the equilibrium constant expression according to the equation given, okay, and you get the answer. Okay, so this is another type of problem. Okay, so this lesson is very important for problems. Okay, so you have to practice some more problems from an NCERT book or from a NEET practice book. Okay, okay, so I'll stop here, right? So this is the first part of equilibrium. Okay, first part of equilibrium I have completed. Okay, please watch this space. Okay, the second part is coming on chemical equilibrium in a short while. So you can watch this space for videos on chemistry. Okay, right? So second part of chemical equilibrium video will be presented shortly. Okay, so please watch this space for videos on your NCERT chemistry lessons. Okay, thank you.